Hello everyone. This is now Sudenaz Sunsal will give us a speech. She's my mentee. She is a mathematics student in İzmir Yüksek Teknoloji University. She studied Simon's algorithm. It's an algorithm that is difficult for classical computers but has efficient solution in quantum computers. Now the stage is yours.
Thank you. So we are going to start with the contents. We are going to start with the motivation before the problem. And we are going to look at our problem. Then we are going to examine the classical solution. And before the Simon's algorithm, I'm going to give you some background for quantum algorithm. And then we are going to see the quantum solution or Simon's algorithm. So the motivation is Simon's problem classically solved exponential time, which is bad for computers, and also it is lower bound. But with quantum computation, it can be solved in a linear time, which is good for computers. And also, let me remind you, big O means that the number of computations required to solve the problem is n up to a constant factor. So the problem is let f be a function from n bit strings to n bit strings, that f is a 2-to-1 function for different two inputs. Let us say x1 and x2. They are going actually the same output. So f is 2-to-1 function, and for all x and y is an element in n bit strings. So f of x is equal to f of y if and only if x is equal to a, x, or s. For some s is an element of n bit strings. The problem is find the secret strings as computed f of x. To solve this, we need to find a collision which is a pair such that x1 is not equal to x2 and f of x1 is equal to f of x2, since x1, x, or x2 is equal to s. And I need to remind that XOR is actually bitwise addition modulo 2. Now we are going to examine the classical solution. So we have a set R is be the randomly taken subset of inputs from x1 to xm. Our aim is defining the value of m in terms of our problem's parameter n, so that we will have a collision with high probability. The probability of xy, xj producing a collision is 1/2 to the power n minus 1. And the number of pairs in the set R is m choose to m times n minus 1/2. Hence, the probability of a collision in the set R is their multiplication, which is approximately m squared over 2 to the power n. And having a collision with high probability means this probability to satisfy 1. And also, this is the lower bound. Thus, we have exponential complexity, which is bad for computers. Now, before our quantum solution, I'm going to give you some background for quantum algorithm. So what is qubit? A qubit is a quantum information unit whose state is represented by the linear combination of qubit 0 and qubit 1. So we are seeing, you are seeing psi is equal alpha 0 plus beta 1, where alpha and beta are complex numbers, and alpha squared plus beta squared is equal to 1. We are going to say that these states, or qubit 0 and 1, we are going to call that computational basis of complex space or two-qubit system. If both alpha and beta are not equal to 0, we are going to say that qubit is in a superposition. And a measurement is a way to read a qubit state. A measurement of a qubit in the computational basis gives the result 0 with probability alpha square and 1 with probability beta square. Now we are going to look at the operations. A measurement is an example of an operation on a qubit. You are seeing the symbol in here in the circuit. And another type of operation is unitaries, or we can call this gates in a circuit. Any change of a qubit states can be represented by a matrix in 2x2 matrix, which entries complex numbers. And also, the matrix defines an operation on qubit state. They are the building blocks of quantum algorithms. For example, Hadamard gate. Actually, Hadamard gate, when we apply the Hadamard gate to the computational basis states, it creates an equally weighted superposition. When we apply Hadamard gate to the basis state, one of the basis state 0, we get 0 plus 1 over square root of 2. And the other one, when we apply 1, we get 0 minus 1 over square root of 2. Now, multiple qubits. So we have a 2 qubit in the two qubit system or complex space. One of them is psi 1, the other one is psi 2. If you want to find the state of the system, we need to take the tensor product, which is the 4 qubit system. Now psi 1 is equal to this: alpha 1 0 plus beta 1 1, and alpha 2 is also alpha 2 0 plus beta 1 1. If we get the tensor product, we get this equation. And we can say this right now: the corresponding computational basis states are 0 0 0 1 1 0 and 1 1. And also note that so that in here we have 3 expressions. Actually, all of them is the same. So tensor product 0 and 1 gives, we can write this like this, and like this, it's the same. And the operations. So we say that there is an operator A, and we want to apply to the two qubit system. We can express this like A psi 1 tensor product, A psi 2, for example. So this is actually equal Hadamard 0 times Hadamard 0, and it's actually equal 1 over 2 sum x. X lives in 2 qubit system, or we can easily generalize to a system of n qubits. Now CNAP gate. CNAP gate is very useful gate on 2 qubit system. There is a 2 input qubit. One of them is control qubit, and the other one is the target qubit. We can describe the action like this. So if control qubit is 0, then the target qubit is left alone. If the control qubit is set to 1, then the target qubit is flipped like if our control qubit is 0 1, let us say. Then we apply control CNAP gate. This is actually cool. But if our control qubit is 1 and target qubit is 0, yeah. Target qubit is 0. So how we evaluate a classical function with qubit and quantum gates or quantum circuit? Given a classical circuit for computing f, there is a quantum circuit of comparable efficiency which computes the transformation UF on a quantum computer, which we're going to call this black box. And now UF in a circuit works very similar to CNAP gate, namely the control qubit is in the input register and the target qubit is in the output register. Our input register is XY qubit, and we get X, Y, XOR f of x. For example, if we say Y is equal to 0, then we get X f of x qubit, because 0 XOR f of x is equal to f of x. Now the quantum parallelism. Quantum parallelism is used for building quantum algorithms that are more efficient compared to their classical counterparts. Now assume that we have a classical algorithm that n bit strings to n bit strings. We're going to set this to 1 because for simplicity, we can take a superposition of 0 and 1 as input and evaluate both values concurrently by running f for once. When we run, the resulting state will be the input and output tensor product. But when we run this, actually we are not getting the results separately. So this does not necessarily mean we can read both f of 0 and f of 1, but still useful. So now we are going to look at the quantum solution. So you are seeing a circuit, how to read a circuit like this. So we have a first register and a second register. When in Psi 1, we are going to apply Hadamard to the first register. And in Psi 2, we're going to apply to the both register, UF. And then in Psi 3, we are going to measure the only second register. And Psi 4, we are going to apply Hadamard again to the first register. And then we are going to measure. So recall our problem. So sinus problem is actually there is a function from n-bit strings to n-bit strings that is actually a 2 to 1 function for all x and y. If f of x is equal to f of y, if and only if x is equal to y XOR s for some s in n-bit strings. We need to find s. To do that, we need to find a pair such that x1 is equal to x2, and f of x1 is equal to f of x2 since x1 XOR x2 is equal to s. Now in the following, we will omit the normalization factors for simplicity. And we are going to set n to n is equal to and consider f is 2-bit strings to 2-bit strings or 2 qubit system to 2 qubit system. So if this answer is actually is equal, in the beginning I said that this is the first register and this is the second register. To show that I separate it like this, this actually is equal. In Psi 1, we are going to apply Hadamard to the first register or our input register. And we are applying Hadamard to our first register, and we get some x in 2-qubit system. X tensor product 0 square or 0 0. Now the first qubit is changed, but the second one is second register is the same. And for Psi 2, we're going to apply UF the both register, input and output register, and we get this expression. Now we need to measure this, but we know that since f is 2 to 1 for each x, f of x has 2 preimages, namely x and x XOR s. When we apply measurement on the second register, it collapses to a state f of a for some a. We get this expression. And now we actually measured the second one, so we are going to omit it. We are not going to see that. We will ignore the second register qubits and apply Hadamard on the first one again. When we apply that, we are going to get this equation. And we are going to do one more thing, that we are going to take the common factor. And this is very important for us because we are going to focus to the power of the -1. So observe that since s times y is a power of -1, we only care if it is 0 or 1 from root 2. So if s times y is equal to 1, then the qubit y disappears because their coefficient becomes 0. And then if s times y is equal to 0, then qubit y survives. Actually, such y's are the only surviving terms in the state of Psi 4. And hence, when we apply measurement, the result will be some y such that s times y is equal to 0. Repeat this approximately n times, and we get s times yi is equal to 0 for I is 1 to n. Solving this linear system of equation will give this. And actually, we solve this. So f is computed n times, and this algorithm has complexity, exponential, and we get linear time. So our problem is done. This is my references, and this is the end of my presentation. Thank you for listening.